Hello everyone. Today we're going to talk about our first type of compounds called ionic compounds. Now with ionic compounds there's a couple different rules. So as you see on the slide, we're going to start with the binary ionic compounds first, which means two elements only. Oops. Alright, so with ionic bonds, we're going to start with these ones first, and then in a couple videos you'll see a video on molecular bonds. Then you'll see that type. So first we're going to start with this very first ionic bonds with metals and nonmetals. Now there's a couple different types, metals with polyatomics, polyatomics and nonmetals, and you can even have two polyatomics together. Okay. The key part to ionic bonds, as you see in the little video clip right there, is a metal versus a nonmetal. They do a little communication, kind of a little dance with each other. Somebody has maybe too much electrons, somebody doesn't have enough electrons, so they help each other out. So it's what they call the loss and the gain of an electron. So metals, right there, the blue, sodium right there, the electrons, the metals will always lose electrons because they do not have enough valence electrons to complete their orbitals. They're not even close. Most metals have like 1, 2, 3 valence electrons the most, couple 4. But nonmetals have more valence electrons, usually 5, 6, 7, because they're trying to get to that 8 valence electrons to have that complete octet shell. So as you see right here in the little simulation, when the metal loses, it will become a positive charge. And when the nonmetal gains the electrons, it will create what's called a negative charge. Okay? So as we go through here, pay close attention to which type of metals like to lose and which ones like to gain. So in here, as you see with sodium chloride, okay, what happens with protons and electrons, when the atom's neutral, as you see right here, 11 protons, 11 electrons, when the atom's neutral, they're the same. But if sodium loses an electron, notice what happens to the electrons. You obviously decrease. Now the protons and electrons are not the same, so you actually have less electrons than protons. On the flip side, with chlorine, you have 17 and 17 because it's neutral. Well, because sodium gives 1 electron up to chlorine, you actually have 17 protons, 18 electrons. So you have more electrons than protons in that case. So on the metal side, you will have less electrons than protons. On the nonmetal side, you'll have more electrons than protons. And there is that bond right there. It's an electrical attraction between the metal and the nonmetal. So an ionic bond, that electrical attraction between the ions. It's not an attraction between the atoms because the atoms haven't lost anything or gained anything. Once you lose or gain, then you become an ion. So an ion is a charged atom. And there's two types of charged atoms. You have cations and anions. The cations will always form positive charges, and the anions will create negative charges. So the electrons are taken by one atom and given to another. It's kind of like a magnet, north and the south pole. Very key here, why we call ionic compounds salts, because they contain a metal and a non-metal, positive and negative type of charge ions in those formulas. No matter who the ionic compound is, it's always a salt. Just like sodium chloride is a salt. Magnesium sulfate is a salt because there's a metal, positive, and a non-metal, negative, or polyatomic negative that creates that salt. So one side of the periodic table loves to lose, and that's the metal side. And I'll put a periodic table up in just a second. So the metals lose electrons, become positive ions, aka cations. I've heard students before in the past say cation. No, just break up the word in half. You got cat and then you got ion. Okay? So like for example with naming, it gets a little tricky in the beginning. When you name them, it's sodium atom. But as soon as they lose, you have that +1, and when you write a charge, you write it kind of like a little exponent in the corner, as you see right there. Corner on the right side, and when you do, you don't have an atom no more because it's not neutral no more, because now you have less electrons and protons, so now you have an ion. So it is very important that you understand the difference between an atom versus an ion. So what side of the periodic table likes to do what? So if you have your periodic table, okay, or push pause and go get it, you're going to want to label your periodic table the following groups and who does what. So we're talking about the metal side first. And remember, the metal side is this side of the periodic table. Okay? So on the metal side, everybody in group 1, they only have one valence electron. And because they have only one valence electron, they will only lose one. Okay? So everybody in this group, even hydrogen, that's why hydrogen's sitting over there, because he has one valence electron. So everybody up here will have a positive charge. Okay? We don't talk about francium too much until we get to the nuclear chemistry type of topic chapter. Because francium is radioactive. So we're just only going to talk up to cesium in this respect. Group 2, they got 2 valence electrons. Okay, and if you even want to label that 2, that would be good. So 1 valence electron, they have 2 valence electrons. So because they have 2, they can lose 2. Okay, so as you see the different symbols right there. Same thing with radium. We will talk about that one later. But it potentially could also, on paper, also lose 2 electrons. Now, we're not going to talk about the transitions, because the transitions is a different video coming up, where these guys can pretty much do a lot of things. They can lose pretty much as many electrons as they want, sometimes 1, 2, 3, maybe 5, 6, whatever they want to lose, to become a stable type of ion. But like I said, that will be another video coming our way. So we're going to jump all the way over here to group 13, or as we like to also say 3A, because that 3 means that they have 3 valence electrons. Okay, so everybody in here, even boron being the only non-metal that is in here. Actually, I'm sorry, he's a metalloid. Even the metalloids can also have those +3. So they have 3 valence electrons. Once you get down past aluminum, so from here on, they can have other charges. Okay, don't memorize them. You'll be able to figure out what other charges. But they're normal, pretty typical type of charges +3. But they do have others. So from gallium, indium, and thallium, there could be others. Okay, because remember, you got the staircase that sits, where is it, right? Yeah, right here. Right there. There you go. Sorry, took me a little moment there. You have your staircase sitting right there. So pretty much anybody under the staircase can have other charges. But beware, aluminum, only +3. That's it. That's all he has. So we can go one more, +4. Okay? So even carbon. Carbon's a nonmetal. Carbon's very special. We'll get to him throughout this course. Carbon has his own chemistry called organic chemistry. And who says he wants to lose 4? Maybe he wants to gain 4. He can actually do both. Okay? So, but for typical sake, he has 4 valence electrons. No matter what, he has 4. But if he does lose, he will become, as you see, a +4. So everybody under here, once you get to germanium and going down, germanium down, they can have other charges. Okay, typically we would see 10 like +2 or +4, lead +2, +4. They do have other charges. So if you also want to list that on here, so +2 also. Okay, same thing with gallium. Sometimes he likes to be +2. And indium and thallium, I'm going off of memory here. I know thallium +1, and then indium +1 and +2. Like I said, there's no point to memorize them because you'll be able to figure it out looking at formulas. So once you get to that part of the periodic table, then they start to like to gain. Okay, so metals, oops, I should say non-metals. Gotta fix that. Non-metals like to gain because they are so close to that octet rule. If you got somebody with 6 valence electrons, it's not going to lose 6. It just needs 2 more to get to that octet, that 8. So nonmetals like to gain electrons. And when they do gain, they become negative ions, as you see anion. Just like cations, just break the word up into 2, so anions. Here's a little tricky though. The name changes when you gain. So when you gain electrons, instead of the name atom versus ion, just a simple slap on a new name, you got to change the ending of the nonmetal name. So I put an example here, like chlorine atom hasn't even gained anything. But now he gained 1 electron, and check out the ending is now chloride. So I put a list up here to help you with spelling. I'll put it up here in just a second. Let's label our periodic table where this starts. So we just left off with carbon having 4 valence electrons. So now we're going to start right here. And everyone past this line, they will gain. Now some of these down here, because they're metals, they will still lose, okay, but all the nonmetals will gain. So remember, we have that staircase going right here, okay? So everybody above here will gain, but you do have some of them down here that will still lose. Like antimony is +3 or 5 most of the time. Same thing with bismuth, +3 and +5. We will hardly talk anything about polonium until we get to like the nuclear chapter, so I'm not going to worry about polonium. But everybody in group 5, because they have 5 valence electrons, they will gain 3 electrons. Now check out the endings, okay? Like I said, there's a chart coming to help you with the spelling, but nitrogen becomes nitride, and phosphorus becomes phosphide, and arsenic becomes arsenide, okay? So right here we have 5 valence electrons. We're going to go to the next group, group 6A or 16. We got oxygen's group. Now we have more nonmetals here, okay? Because remember, the staircase is down here, right there. So we can actually go all the way down to tellurium if we want. So we have this group has 6 valence electrons. You list it up here. And with these ones, because they gain only 2 to get to that octet rule, same thing with their names, they change the ending. So oxygen becomes oxide ion, and sulfur becomes sulfide, and selenium becomes seleniide. I could even do tellurium too, telluride. Okay, I just didn't list it up here, but it could do that. And the very last group, the halogens, the most reactive nonmetals, these are like your salt makers right here. All of these have 7 valence electrons. So they are so close to that 8. They just need 1 more. So you know you're not going to get that loss of 7. They only just need 1 more. And same thing, you got your staircase that hits right here. So we're not going to talk too much about astatine that's down here, AT. So fluoride or fluorine becomes fluoride. Be very careful with the spelling. You would be probably shocked at how many students spell fluoride as flouride, okay? It's U-O, not O-U, like flour that you bake with. Chlorine becomes chloride, and bromine becomes bromide, and iodine becomes iodide. Now, the very last group, the noble gases, they already have their complete octet, except helium. He only has 2, but he's still complete. They don't have any charges, okay? So not one of these elements have any charges. They do have, well, starting right here, they do have 8 valence electrons. Helium only has 2. But no matter what, they're complete. They're not going to form any charges. Now, I didn't say they don't form any bonds, because we got a couple of these sneaky guys that do like to bond with fluorine. Once we force it to, we can't actually successfully get a couple molecules with fluorine out there. But I would not worry about any of these. We will not be writing any formulas with these guys, unless we talk molecular, but nothing with them with ionic. So just to recap your periodic table, you got your first group, group 1, and then the second group, group 2. I don't know why they didn't shade in beryllium, but we also can do beryllium. We got, like I like to call this, crazy town in here. But I will label 2 of these to help you. Silver and zinc, they don't have any other charges. It's about the only transition metals out there that pretty much only got 1 type of charge. So silver, you may want to label your periodic table. Silver will always be +1, and zinc will always be +2. And I always remember this little trick I show my students. Right there, the zigzag. 1, 2, 3. It's a really, really cool trick to it. There's a lot of tricks in the periodic table to help you learn it, not memorize it. But remember, you always have a periodic table, but you do have to know which groups do what charges. Group 3 loses 3, and group 4 loses 4, and as soon as you get right there past that carbon, then they start to go negative, okay? Now remember, down here, they do have positive charges, because those are metals. Metalloids right there, they can have positive or negative, And then obviously all the nonmetals have negative. And we will not, like I said, be talking about the noble gases and ionic. So here's kind of a little movie to help you figure out what's going on. The metal comes along. Think of it, sodium. Sodium has an extra electron. He's nowhere close to that valence electron. Chlorine, green one, got 7, needs just one more. But look what happens to the size of them. One shrinks. One gets bigger. Okay, let me go back so that way you can see that again. So because the sodium has an extra one, he gives up an electron, he gets smaller. I mean, it makes sense. And the chlorine needs one more, he gains one, gets bigger. Okay, should make sense. So when they come together, the key part to this, it's an electrical attraction of opposites attract. And because the transferring electrons produces from these ions, you have what's called ionic bonding. So the force that holds that positive and negative together, it's an attraction, like a magnet. The north and south pole, it's a magnet. So they are held together by that attraction. So this is what salts look like. Salts have what's called a crystal lattice, and we'll learn about that when we talk about states of matters for salts. They have this three-dimensional repeating pattern. That's why they're called crystals. And this is what they look like under the microscope. Beautiful, beautiful crystals under there. And as I said, all ionic compounds are salt. No matter who the salt is, they're all salts. Okay? So when you are writing formulas, we're going to get down to the rules now. Binary ionic compound rules. So one key word besides binary, one key word that you need to understand first is what's called monoatomic. Mono means one, atomic means atom. And the word obviously ions means with the charge. So you have one atom with the charge. So whether it's sodium plus 1, oxygen negative 2, it doesn't matter who it is. You only have one type of it with the charge. Now binary means 2. Okay, some prefixes like di means 2 also. Bi means 2. Chemistry uses bi sometimes and di for other things. Binary means only 2 monoatomic ions, so a metal and a nonmetal. So if I put these two together, then that would be a binary ionic compound, but it came from 2 monoatomic ions. Very simple rules. Ionic compound students do very well with ionic. You just need a periodic table. So write the cation first, that's the metal, and write the anion second. Done. Make sure you write the charges with the numbers that go with it. The net charge of the whole compound has to be 0 because ionic compounds are neutral. They have to equal 0. So 1 minus 1's got to equal 0. 2 minus 2's got to equal 0. But what if you get in trouble? It's called step 3. It's called the crisscross method. Okay? Cross the numbers on the charges only using subscripts to balance it out. And I'll show you what I mean by that, okay, as you see an example. We don't ever write the ones. As I said, it's tedious. If it didn't have 1, you wouldn't have wrote the symbol to begin with. So here's an example, sodium chloride. Sodium's group 1. I already put the charge for you. Chlorine negative 1. When these two come together, because sodium lost, chlorine gained, when they come together, you're going to get that neutral charge, that electrically neutral charge. I didn't have to use step 3. I didn't need to crisscross anything, okay? But what if I had barium and I had chlorine, okay? Barium loses 2, but chlorine gains 1. But it still has to equal 0. So what happens is you can't lose barium, but you can gain another chlorine. So if you add another chlorine, well, negative 1 and negative 1, that equals negative 2. And that gets you to neutral. Well, instead of doing all that work, quick little trick, the crisscross, if you cross only the number on the charge, cross it down to make it look like a subscript, and then obviously take the 1, same thing, cross it down, but we just don't write the 1s. So then you get BaCl2. I have a 1 to 2 ratio, 1 barium for every 2 chlorines. Okay, very simple. When you name them, you got to remember the atom that gained to become an anion changes the ending to IDE. So this is called nomenclature. Nomenclature is a fancy word that chemists use for naming compounds. Okay, so you will see this word nomenclature a lot throughout the videos, and so please make sure you understand what nomenclature means. Fancy chemistry word for naming compounds. Okay, so sodium lost. Name doesn't change, But because chlorine gained, the ending changes to IDE. Okay? Same thing with barium. Barium lost, still barium, but the chlorine gained, so now you have chloride. So I always get this with students. Well, what about the two? Don't you have to say like dichloride because you got two of them, or bichloride? No. No, you don't. It doesn't matter how many you have. It's all about the charges getting to equal 0. Now, there is a type of compound out there in the world called molecular, where you do actually have to name how many you see in the compound. Okay, but right now we got ionic binary compounds. So I put this in the notes to help you with spelling till you get the hang of it. Like I said, pretty much the common misspelt one is the fluoride one. Okay, but be very careful with hydrogen. Okay, I'm going to list this in here. Hydrogen only has 1 electron. Who says he wants to lose? Typically, most of the time, he becomes +1. He loses because he only has 1. But who says he doesn't want to gain 1? He can do both. But when you lose, well, the name doesn't change. You still got hydrogen and then ion. But what if you gain? So if you gain that electron, you have to change the ending no matter what. So that's called hydride. Okay? So very few elements out there can actually do that. Like I said, carbon can do that. Some of the metalloids can do that. They can either lose or they can gain. Okay? So let's do a little bit of practicing. So first what we're going to do, this time I left the symbols and the charges on it. Normally you guys would be looking up the charges for yourself. Okay? So sodium +1, sulfur -2. So we're going to write the formulas and the names. 1 and +2, and usually we write the ones. 1 and -2 doesn't equal 0, so we're just going to crisscross, bring the 2 over, bring the 1 over, and this is what we call showing your work. So now I'm going to get sodium, bring the 2 subscript, and then the sulfur only has 1. Now remember, when they lose, you do not change the name. And you don't have to capitalize element names either. You just got to spell them correctly. So sodium and sulfur becomes sulfide. Okay? Aluminum lost 3, chlorine gained 1. Doesn't equal 0. It's not neutral. So we're going to crisscross. So I'm going to get aluminum 1 and chlorine 3. So aluminum. And just a little side note on the spelling. For aluminum, a lot of the elements on the periodic table have an ending of IUM, 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 not aluminum. It doesn't have that I at the end. Okay, so just NUM at the end. Magnesium lost 2, nitrogen gained 3. Okay, so you could actually crisscross, and when you do your crisscross, you could actually have 2 subscripts appear on a formula, and nothing wrong with that. So magnesium 3, nitrogen 2. So we don't have to name how many we see. We're just naming the elements that are involved. Now nitrogen becomes nitride. Same thing, aluminum lost 3, sulfur gained 2. So aluminum 2, sulfur gained 2. And I have my aluminum. And then sulfide. So notice right here in the first example with 1 sulfur, this fourth one with 3 sulfurs, it's okay. It doesn't matter how many you actually have. It's still sulfur, still sulfide because it gained from the metal. Zinc +2, iodine -1, same thing. We're just going to crisscross to make that neutral. So Zn and then the I2, so zinc, and then iodide. And the last one, calcium +2, -2. What if it already equals 0? No need to crisscross. Don't crisscross, okay? Because there is a law out there called the law of definite proportions. You need to keep your subscript as lowest possible ratio to be, like 1 to 1, 1 to 2. Okay, same thing as a topic you're going to hear about later on in the course called empirical formula, the lowest possible ratio. So if they automatically equal 0, they cancel each other out. No crisscross necessary. So calcium and the oxide. Okay. All right, one more set of examples. What if you have to write the formula from the name or the name from the formula? Okay, so in this case, you will need a periodic table to do this. Okay, so that's why it's very important that you label all the different parts to it. So Ba, I2. So I know Ba is barium. And iodine becomes iodide. Okay? But now if you have the name, okay? So this is what's called showing your work. Show me before and after. So the before is, what's the charges? So sodium, I know, according to how I labeled it, I know sodium loses 1 because he has 1 valence electron. So it's +1. Phosphide, according to my periodic table, will gain 3. So when they come together, crisscross, I'm going to get that Na3 and then P1. Okay. As you go along through it, you don't need to show me the actual arrows of crisscross. That does take time, especially in AP. Don't take that time to do it, but always you have to show me the work. Okay. Always show the work of the before. What are the ions before it makes that ionic compound? Aluminum is our metal, and 3 fluorines, so we have fluoride. And we have Ca, which is calcium, and we have Se, which is seleniide, okay, from selenium. Sodium nitrate, we already know sodium +1. Now nitrogen's in the same group as phosphorus, can gain 3. Okay, same thing as the second one, crisscross. So I'm going to get my sodium 3 and then 1 nitrogen. The next one, K is potassium. And then Br came from bromine, but it gains, so now becomes bromide. Aluminum, Al +3, because he's in group 3A, he's got 3 valence electrons. Oxygen, a couple groups over, gains 2. It's not electrically neutral, but you do have to not only crisscross, but crisscross both of them. So now aluminum has 2, and oxygen is 3. And the last one, we have magnesium. Sulfur gains, so it becomes sulfide. Okay? Once you get the hang of this, ladies and gentlemen, it's a piece of cake. So these are the rules for binary, only 2, metal and a non-metal, for binary ionic compounds. Hope it helped, ladies and gentlemen, and see you on the next one.